Ok, estamos lá.
Boa tarde a todos. Boa tarde aos que nos acompanham pelo YouTube. Hoje a gente dá continuidade ao ciclo de seminários do Departamento de Estatística da UFRN. Eu me chamo Andressa, sou professora do Departamento de Estatística. Hoje nós teremos novamente a palestra do professor Weibull, né, na última palestra.
Ok, estamos lá.
Ele começou a aula dele na última palestra sobre a regressão Weibull, o professor Weibull, sobre a regressão Weibull com aplicação na contabilidade, e hoje será a segunda aula. Então, thank you so much, Professor. Thank you for sharing your experience with us.
Having fun. This is my summer vacation. I'm having a blast. This is good. Okay. Do we have something to write with? Yeah. The first lecture had two purposes. One was to introduce the Weibull distribution. That's the first purpose, but the second was to introduce censoring. And censoring is pretty unique to, well, it's important in biostatistical applications because of patients coming in and out of a study. But it's absolutely fundamental when we're dealing with industrial reliability experiments, because generally the time frame is too short to allow people to see the failures that could happen. So you take advantage of the failures you can see, but you have to take into meaningful account the failures you could not see because you had to stop the test. That was the purpose of the first lecture. So far, so good? The second lecture basically we're doing simple linear regression. In our reliability context. What do I mean by that? Okay. So just as a preface. In this lecture, we're going to be dealing with an X, which will be stress. Okay? So we're going to apply stress to test items. We will be dealing with a real NASA experiment with cord, yarn. We're going to put weights on that. We're going to put a tensile load on that. And we control the X. See? So we actually control this. We're going to observe, and I'll use it as a T, time at failure. This looks like simple linear regression, right? This is the Y, we have the X. So we'd be looking at something that T is like a, I don't want to use that, alpha naught plus an alpha 1 times the stress, dx here. So far, so good? And normally we would have an epsilon out here. We don't have any Weibull regression. So far, so good? And our goal in simple linear regression is, given the X, is to break T, right? Not in what we're doing. Our objective is to find what's the probability it will fail at time T. So what we are trying to do is predict, in this particular case, in Weibull regression, we see the model the probability of failure. Are we seeing how this is different? There are similarities, but they're not all there, okay? There are some significant differences. My focus ultimately in my NASA experiment is to predict probability of failure at the specified use stress for the expected life of the mission. My goal is not to predict the time. I'm trying to predict the failure at a time at a specific load. This is much more complicated, but it's not that much more complicated. That's where I want us to see. But so when I start talking about this is simple linear regression, basically it is, but it has some differences to it. And that's what I want us to appreciate. This lays the foundation for next week's lecture, where I will take you into a controversy, big time controversy. One where it will be an earth-shattering result in the subject matter area. And I want us to appreciate what's going on there. So far, so good? Are we understanding from where I'm coming? This is going to look like simple linear regression, and it's good to interpret it that way. The reliability engineers have no idea we're talking about simple linear regression. Okay? For them, simple linear regression would be to predict the time. And they say, I don't care about the time, I care about the probability of failure at that time. Notice how it's different. So when I start dealing with the engineer, and I start talking about this as regression, they look at me with this look of, what are you talking about? From what planet did you come? Okay? Because that's not their world. But it is their world and they don't realize it. So far, so good? So when I talk about simple linear regression, we're going to go a few levels beyond what you would teach in an introductory class. Fair enough? Okay? And that's going to be very important as I start creating more and more tools. Meeker and Escobar, it's now Meeker, Escobar, and Pascal, is the definitive book for analyzing, doing statistical analysis of reliability data. Bill, Louise, and I don't know the third author, really don't understand regression very deeply. And they don't have to. I'm going to touch on areas in regression you will never see in a reliability textbook. But it goes back to how do we really do regression analysis? What's the real theory underlying it? I hope I'm making sense. And that's going to lead to some radically different ideas that the reliability community do not understand, but are straightforward once we see what's going on. That's my goal, okay? So with that, let's go ahead and get into the slides. So the engineers will call the model we're playing with a classic power law model. And in fact, within certain communities, they will call it the stress rupture model. This is from the engineering perspective. By the way, the discipline of reliability is dominated by engineers, not by statisticians. So the quality of the ability to do data analysis varies widely, okay? So classic power law model, what I'm going to show you is basically a linear regression model. And for them, it's always the simple linear regression model, okay? I'm going to talk about estimation and testing, and I'm going to take this perspective from the, I will be looking at this as a regression person. I'm extremely well trained in regression. I'm co-author of 2 textbooks in regression. I got that one down. I teach linear models there, okay? I've had to learn reliability. Reliability depends on math stat, usually mathematical statistics, usually at the level of a master's course in a good graduate curriculum. They don't talk much about regression in there. They don't really talk much about how you do testing from a regression perspective. It's mostly estimation, and then they talk a little bit about likelihood ratio test on parameters. So far, so good? My interest is testing models. We don't talk enough about that in mathematical statistics, yet that's what we do in regression. We're testing what is the best model to explain the data. Parameters are important in that, but we have to understand what would be the full model for the data. I don't see that conversation very often in master's level discussion of mathematical statistics, yet it is very fundamental in regression, and you see this in generalized linear models to an extent. So far, so good? Okay. I'm going to do everything in terms of this real NASA example. There are benefits to that because this is real, the data are real, all of the analysis are the analyses we're doing in our report. I cannot share with you parameter estimates. I cannot share with you, I can share you the levels we're using, but they're standardized levels. Am I making sense for people? We hope that we expect to be able to publish everything in the general literature, but we have to get a formal approval from NASA to release the parameter estimates, to release what the material is. I gave a talk at Rafael in Israel, one of the big defense contractors, and they deal with aircraft and with missiles. Carbon overwrapped pressure vessels was very interesting to them. When they heard my example dealt with carbon overwrapped pressure vessels, a lot of engineers came. I wanted to talk about statistics. They wanted to talk to me about the properties of the material. What was the material and what were the properties? And I had to say, I can't tell you. Okay? And how many times did I have to say, I cannot tell you? Probably 15. Okay? So let's appreciate from where I have to come. Also, I'm going to introduce residual plots that I have not seen anyplace else. Meeker and Escobar in their 1998 book talk about, oh, you can do all sorts of analogs to the regression residual plots. They don't show any, okay? You go into Minitab, they don't do any residual plots. So this is a new contribution, okay? Not that it's rocket science, it's not. It's just very straightforward and simple. So far, so good? That's where I want to go today. Next slide, please. I'm going to let SI be at constant stress, and it has to be at constant stress in this, because we're doing this over time. So if that stress is changing, then that's a dynamic system, and it's not dealing with constant stress. We are assuming the item is under constant stress, or effectively constant stress. That's the basic premise of this test. I'm going to let S sub ref be a reference stress level, and I will begin to explain what that means as we go along. Ultimately, it's designed to create a dimensionless number, which we will call a stress ratio. So all this SREF does is standardize our stress so that it has some interpretation. That's important for generalizing results. When we're dealing with carbon overwrapped pressure vessels, we don't necessarily know what is the actual strength that they're looking for. So what we do is we give them a standardized measure that they can then scale accordingly. Often, this is the use condition, and the stress is something much larger than that. So usually, if you go and see in the literature a stress rupture test, you will see stress ratios that are larger than 1. Why? Because then they will project back, extrapolate to the use condition. This makes it easy to interpret. So far, so good? Because we do not care about the probability of failure at an elevated stress. We care about it at the use condition. What are you taught in all your statistics classes about extrapolation? The answer is, don't even think about doing it. That's wrong, by the way, but not far wrong. When you think about a planned experiment, you have two levels. You have them at extremes to each other. So far, so good? And you're going to estimate simple linear regression. Where's your best prediction? Is it at the extremes or is it at the very middle? It's at the very middle. Do you have any data there? The answer is no. You're relying on your model. Now, all of your data are at the extremes. So if you go just a little bit beyond the extreme, is it going to have a big impact? No, because you're still near your data. But the further you get away from the data, the worse your probability of being able to understand the thing go well. The confidence intervals go wide. Are we getting the picture on this? Okay. Often with these reliability experiments, you're dealing with things that could be very far away. The use condition could be very, very far away from where you're doing the test. I'll remind me and I will explain that as we get into the NASA exam. So far, so good? Extrapolation, but extreme extrapolation. Next slide, please. T will be the characteristic of interest. Eta, I used eta for the characteristic life in the first lecture. We'll still use that. So it's the characteristic of life associated with that particular stress ratio. And this is the classic power law model. It's in this form right here. Okay? Now, I think I showed that in a slightly different form, and that will become important. But if not, I'll put it up here on the board. It's called a power law because it's in terms of this parameter P. This parameter rho, sorry. So I have this parameter rho is in this form. That looks very funky. That does not look like simple linear regression, does it? What happens if I take the log of eta? Oh my. Okay. So this is relating it back to the Weibull distribution, the Weibull distribution parameters. This is a power law in it because of this term here. Okay. So we are raising that stress ratio to the negative of rho. And again, what we're testing is the ability of a test item to support a constant load. If you think about on a mission, the pressure vessel should be at that load until it needs to be used, in which case it will go down. But that's the goal, getting maintain the desired load. So far, so good? Next slide, please. Here's the survivor function. This is how the engineer thinks about it. The engineer sees the survivor function. The engineer understands the survivor function. Doesn't care about any relationship to simple linear regression. Doesn't even realize it's there. So far, so good? This is coming back to the probability. Remember, I said our goal is to predict probability of failure. There's the survivor function. The ultimate goal is what's the probability of surviving at the use conditions for mission life? Our interest is that survivor function. Okay. Now, playing with this, I can re-express it like this. And when I first saw that, I said, why do I want to do this? Why do I want to go e to the minus e something? That just seems like I'm making it more complex. Oh, no, I'm not. But I hope you begin to see this. It took me a while. If we look at this in the proper fashion, what are we trying to do? We're using T-ref and the stress ratio and rho to basically come up with, try to predict what would be the expected value for the log time. That's the simple linear equation, simple linear regression relationship. This is controlling location. Beta controls the spread. So this really is, when I call this a residual term, this really is a residual term. But it's pretty simple in respects, and I'll try to show that. I've got a picture coming up to illustrate that. If I multiply it by beta, it's there. It's actually a true scaled residual in the regression sense. How do we scale residuals for plotting in standard ordinary least squares regression? We take the observation, subtract its predicted value, okay? And then ideally we divide by the standard deviation of the prediction. It's scaled. The properly scaled residual would be the externally studentized residual, because that maybe follows a t-distribution. Classic linear models theory. But it's a scaled residual. All the nice plots in regression should be looking at things like scaled residuals. Again, externally studentized residuals. I jump up and down and teach that in my classes all the time. Why? Because it's interpretation of size. It helps us to determine outliers. And by the way, in my universe, the most important piece of data we get are the outliers. It's the opportunity to learn. Okay? Scaled residuals. These are important. These are the things we would like to plot. So when I get to residual plots, we're going to talk about scaled residuals. Okay? Next slide, please. So I'm going to let mu be that analog to the mean value. It's not a mean, it's a characteristic life, but for our purposes, it's useful to think of it in those terms. So that's the reason why I'm using mu. And it's going to be the log of this thing, okay? And lo and behold, mu is log T ref minus rho times log stress ratio I. I define theta, I like theta, for T log T ref. Look at that. That's nothing more than a simple linear regression expression, where instead of an x, we got a log x. Well, that's fine. So far, so good? Just as a quick reminder, what if SI is equal to S ref? The stress ratio is equal to 1. So far, so good? What's the log of 1? It's 0. Theta then would be the characteristic life at the use condition if I define things in terms of the use condition. Are we seeing the value of scaling the stress? Otherwise, T-ref is just kind of a nuisance parameter in the sense of simple linear regression, because we rarely are interested in the Y-intercept. Some cases we are. In this case, I can make the Y-intercept the entity of complete interest. So far, so good? But the point is, expressing it this way, U sub I is the deterministic portion of the model, and it really does represent simple linear regression in terms of the log of stress ratio. I can build more complex models, okay? I can adjust the intercept depending upon different characteristics. Next lecture, I'm going to talk about combining vessels with strands. How will I do that? The hope was there is a common rho and common beta between the strands and the vessels. That all I have to do is to adjust the Y-intercept for vessels compared to the strands. Guess what we were able to do? Okay. Now, difficulty for me working with reliability engineers, they don't understand this, nor do they care to understand it. They're thinking purely in terms of that survivor function, because that's where the probability is. It makes my life more interesting. And I make their lives painful. Are we okay? Next slide, please. here's a plot of what's going on. And the reliability engineer for which I am working calls this a deceptive plot because it's not how he thinks about the plot. But that's because he's thinking about it in terms of probability and not understanding how those parameters fit into the probability calculation. These are the actual failures, actual log times for the failures from our phase B study. There are 48 of them. They're reading, okay? We censored the data at 168 hours. 168 hours, log 10 of 168 is a little less than 2. Are we getting the picture here? Okay. The lower stress ratio, we had a lot of items on it because it's harder to get failures. Medium, and then the high stress ratio level, and they were equally spaced. So far, so good? Okay. T-ref is the Y-intercept. The Y-intercept occurs when the log time occurs when the T-ref is the log time associated with a stress ratio of 0. So far, so good? Okay, so whatever that stress ratio is, let's look at that again. We had the mu sub I. So theta is just the log time associated with a stress ratio of 0. A stress ratio of 1, which would be log of, would be 0. Okay, that's what it is. It literally is a Y-intercept term. And beta is just the variability given the location. This is a log location scale family distribution. It's not a true location scale distribution. It's a log location scale, but it's all the same. But the key is we misteach the Weibull distribution in most mathematical statistics classes because we focus on questions of like, what is the mean and the variance? The mean and the variance depend upon both rho and beta. So far, so good? Both of them do. For the Weibull distribution, the mean and variance depend upon the characteristic life and that shape parameter. You can't separate them. But if we think in terms of the scaling, the log location scale family, then we have the analog, which I've been calling mu. It's like the mean, it's really the characteristic life, but we can think of it in a similar way. So given a value for the mu, the beta is just a measure of the spread. Okay? So if you say, Geoff, for a Weibull distribution, the variance depends upon the mean, it does. So when I talk about variability in terms of the actual structure of the model, the interpretation of beta is variability given a specific value for the location. But now they separate very cleanly. Okay? So far, so good? This is the real structure of the data. Notice that these are the characteristics, this would be the characteristic life at the stress ratio of 0.9. This is the characteristic life, the log characteristic life for a stress ratio of 0.85. This is the log characteristic life of stress ratio equal to 0.8. Okay? We don't have any data near them. If your instinct is that the mean value for your residuals will be 0, that's not happening because we are censoring the data. Are we getting to see how this is different from normal regression? We don't have data out here beyond this. It's centuries away. We can't observe it. So there's a very different intuition as we move into the reliability world. But the modeling aspect of it is very similar to ordinary least squares regression. It's got to guide our instincts. Okay? Next slide, please. Estimation is going to be maximum likelihood. However, now it's a numerical technique. It's no clean matrix algebra to do this. Newton-Raphson is a classic technique for coming up with the maximum likelihood estimates. A lot of software is using non-parametric estimates of the derivatives, but nonetheless, it is an iterative procedure and you have to worry about convergence. Just like generalized linear models. Okay? We can do chi-squared tests. But to do the chi-square test, we got to have a full model. We have to have a model against which we compare. That's where life gets very subtle. And this is where the reliability engineers don't understand a thing that's going on. Their attitude is, if I can estimate the model, it must be correct. They don't know how to compare models. And that's very fundamental for next lecture. AIC is extremely valuable. Yes, there are lots of variants of AIC, but AIC is the easiest to explain, and trust me, in my universe, I don't want to go into the nuances for the reliability engineer who doesn't understand much about statistics, about why is it AIC and not BIC, whatever. It's not worth it. AIC is very simple to explain. It's -2 times the log likelihood plus twice the number of parameters. Simple to calculate. In theory, it's equivalent to mallow CP and ordinary least squares, in theory. It's got a lot of benefits. It's simple to explain relatively, and it's very powerful. One of the things we don't talk about enough in mathematical statistics is that we really have to have nested models for comparison. So if we're going to compare, we've got to have a mother model, which is the full model. So whenever I talk about the mother, there's the full model there. And that's going to be the best we can possibly do in terms of log likelihood. We cannot get better than that mother model. Ideally, it's saturated. In the examples that I'll be using in these lectures today and next time, it's a saturated model. Okay? But we're comparing against that. Subset models can be based on proper engineering theory. They have to be legitimate probability distributions. And I'll talk a little bit about that next time because my engineer friend doesn't know what a valid distribution function is. He feels like as an engineer, he's qualified just to create whatever and call it whatever. It's fascinating. So that's not a trivial issue. So what are we going to do? We're going to get the log likelihood for the mother model, and we're going to compare subset models back to the mother. And if the subset model basically conveys the same information as the mother, we go with the subset model. We can't justify the extra parameters. So far, so good? The most recent version of Meeker, Escobar, and Pascal actually use AIC in these chi-square tests. I was glad to see Bill had done that. And that is actually helping me in working with the NASA people to be able to reference that. Although it's an obvious thing, believe it or not, but it's being able to reference that to the engineer is important. Next slide. Here is the goal of our experiment. We really need to be able to predict as accurately as we can the probability of failure at use conditions and a stress ratio of 0.5, how we defined it. So what we did is we took the characteristic life from the strength data that you saw in the last lecture that defined our stress ratio, and the use condition was defined to be half of that. That's a NASA decision. The expected mission life is 10 years. And the standard at NASA is they would like to make sure that there are 6 nines of probability of surviving. So they want the probability of surviving at least to be 0.999999 at that stress ratio and that mission life. Are we trying to predict a very, very small probability? Yes. Are we extrapolating a very far away? Yes. Are there going to be issues about the confidence band on that prediction? Yes. So far, so good? And NASA talks about things in terms of nines. Ultimately, we got the 95% confidence band to be plus or minus 1 9. That was pretty cool. Okay. Here are the actual results. We had 708 strands achieve their target loads. There were 22 that failed on ramp. So for the purposes of what I'm summarizing in the test, we had 730 test items and 22 died on the ramp. That becomes important next time. We had 708 achieve it, and here is the breakdown. Notice everything is highly, highly right sensitive. Literally, these things die very quickly or they last forever. We censored at 168 hours. That's exactly 1 week. 7 days times 24 hours is 168 hours. So we can turn the equipment around. We had 32 test stands in a facility at White Sands, in between, it's at Las Cruces, New Mexico. And it took a year to run this experiment. Okay? So far, so good? Next slide, please. We can do another model. I can fit 2 parameter Weibull distributions for each one of those stress ratios. Perfectly legitimate. And frankly, that's going to give us the best fit to the data in terms of likelihood. And it turns out that the overall likelihood, because all of these are independent, the way we did the experiment, we independently allocated the test items to the stress ratios. We just restricted how many went to each one. They were independent, so the likelihood for this plus the likelihood for this plus the likelihood for this is the likelihood for the mother model. Going back to basic independence. So the log likelihood is the driver. Independence, they're multiplied. The moment we take the log, they become sums. Life is good. The proper engineering model is the classic stress rupture model, which we talked about. It's basically simple linear regression. Engineers never use the term theta. I'm doing that as a statistician. But they recognize that T-ref is not estimated well, but log T-ref is estimated well. So the focus on the log of that T-ref, that reference time, makes a lot of sense to the engineers. But there are only 3 parameters. The question is, this has 6, this has 3. Do we need the 3 extra parameters here? That makes sense to people? This is an overall F-test. Exactly analogous to it. It's actually a partial F-test, but it's okay. Next slide, please. We are imposing constraints on the model. We're imposing a constraint that the relationships of the individual characteristic lives, okay, the log characteristic life, is just a simple linear regression. So far, so good. So 3 of the parameters are expressed in terms of the 2 parameters theta and rho, and then we're assuming a common beta. Just like in ordinary least squares, we tend to assume a common variance. Okay? Or we're seeing the analogies. It's a little more complex, but the analogies hold. That's important for insight. There's nothing more than the same basic constraints for simple linear regression. And I can expand this. I can add other stressors in here. I can do lots of things. It builds very nicely. This isn't rocket science, okay? So far, so good. Next one, please. As I said before, by randomization, the overall likelihood for the mother is the sum of the individual likelihoods by each one of the stress ratios. I can do this whole analysis in Minitab. I'm going to let this be the likelihood function for the classic stress rupture model. And there we got to go through and evaluate the log likelihood function for that specific model. Okay? Which is straightforward to do. I'm not going into those details. This is the standard chi-squared statistic. But if this log of the stress rupture model is close enough to the log of the mother model, this chi-squared is going to be small in terms of the statistic, and the p-value is going to be large. Which is saying, if this chi-squared statistic is near 0, this is effectively giving me the same information as the mother model. And by the way, the stress rupture model has more information about the nature of the relationship. So we would conclude we need a mother model if the p-value is small. If it's large, then we are accepting that we should go with the stress rupture model. Okay? Basic log likelihood and next slide. The IC is this. Notice the penalty for the number of parameters. That becomes important in this conversation. Again, we're trying to justify, why do I need to go to a more complex model than I need to? Ultimately, that penalty is going back to prediction variance. That would be the proper interpretation of it. Just the more terms you have, if some of those terms are estimating 0, all you're doing is adding variability to the prediction. Are we okay? We can stick any information criteria in there that you want. This is just simple for me to work with the engineers. Particularly since this is easy, we can calculate that by hand. Next slide. I wish I could give you the parameter estimates. I can't. Otherwise, that's all real data. Okay? This is the log likelihood building each 2-parameter Weibull distribution for each stress ratio. And this is that likelihood ratio. This is the log likelihood associated with the simple linear regression model. Not much difference, is there? I get the log likelihood statistic minus 2 times that, subtract it. We're going to get a p-value of 0.7959. Classic case, I cannot justify the extra 3 parameters. Stress rupture model is effectively as good. AIC, it's basically 5 smaller, lots smaller. It's a winner. Okay? This is going to become important next week because I'm going to talk about what the engineer wants to do for estimating the model. And we're going to be looking at the log likelihood statistics, and we're going to be looking at the AICs. For some of the models that the engineer seriously proposes, the p-value is 10 to the minus 62, comparing it to the stress rupture model. There is no evidence to suggest that he needs to go with his model. Okay? It's overwhelming evidence. I want us to appreciate that. We're going to see differences in AIC on the order of hundreds. Right? I want us to appreciate that. Basically, all we're doing is taking a regression problem whose focus is trying to predict not the time that it fails, but the probability it fails. So it's a twist. But I can still get it back into the same basic regression framework, and I can still do things that look like regression tests. But since it's log likelihood based, I don't have an F statistic, I have a chi-squared statistic. Okay? And I don't have R squared particularly, but I can use the AIC in a way that's pretty effective. Next slide. we can come up with a residual plot. So what we can do is the smallest extreme value distribution. So when I say SEV, and I use that abbreviation in lecture 1, but just to make sure. And the parameters are a mu and a sigma. And for the simple scale residual case, we're going to have that the mean, the mu for the log location scale family distribution, the SEV is 0, that equal 1. Looks like a standard normal distribution. And that's convenient. I'm going to illustrate more complex conditions, and Meeker and Escobar in their book from '98 illustrate how to come up with confidence bounds. So I'll leave that. I'll show the formula, but I'm not going to get details on that. Next slide, please. So I'm going to let T sub P be not time. I'm going to let Z sub P be the value of the scaled residual associated with some percentile P. Okay, so the P there is for percentile. T is some time. Z is some value of the scaled residual associated with that probability. This is notation that Meeker and Escobar use. So that's the time associated with that. We can get an estimated SEV location parameter by using the information matrix. Once again, we're doing log likelihood statistics. We are getting the first and second derivatives. The matrix of the second derivatives gives us the information matrix. And the information matrix gives us the variance of our estimate of the mu. It gives us the variance of the estimate of the scale parameter, and it gives us the covariance. Minitab does this very nicely, by the way. Okay? And this is the formula, and this is, again, no rocket science, but I'll leave the details back in from Meeker and Escobar. I just want you to know this is straightforward. And of course, we checked all of our results with Minitab to make sure they were correct. Minitab was a nice security blanket particularly for me. Key is that this is straightforward to calculate once we have the maximum likelihood estimates. Okay, so next slide. Now, this is what becomes interesting. Let's think about a Weibull plot. Of the residuals. So I'm looking at the scaled residuals. So I'm going to have the scaled residuals here. And I'm going to have the empirical probability here. So far, so good? Because remember, we're not predicting the times, we're predicting the probabilities. So all of my residual plots are going to go back to this Weibull plot, but then I'm going to manipulate them so that they become analogs of standard regression plots, because I find them much more informative. So the empirical probabilities are this F hat of T sub I. And how do we do that? There are lots of ways to come up with the empirical probabilities. The reliability community for right-censored data uses the median rank procedure. Meeker and Escobar in their original book took I minus 0.5 or plus 0.05, I forgot which is divided by n. It's not a good one, but this is what the reliability literature uses. And then the software uses Bernard's approximation, so it's the median rank value minus 0.3 divided by the number of observations plus 0.4. This is standard in the reliability literature, and it seems to work reasonably well. So what are we doing? We have a plot then of the F hat T sub I versus the beta T sub I. In theory, it should form a straight line. So far, so good? Okay. So what do? This is straightforward and it will reduce the predicted. This is based on the predictions. This will be the straight line. So then we take the empirical probabilities and we see how they fall around. There's going to be a general pattern like this. And we got all the calculations in there. You can have fun with this. And all the standard software does this automatically for you. What I don't like is it's 95% confidence bounds. Because I'm not dealing with the true empirical probabilities here. Are we getting a picture on this? There's variability associated with this. But Meeker and Escobar are only taking into account the variability around the predictions of the scaled residuals. There's an additional source of variability. These things are not measured perfectly. They're based on what was the ranking. There's a little more variability. So I actually prefer using 3 standard error limits. Not 2 standard error to account for that variability. We also have a fairly large number of observations. So far, so good? Okay. Again, no rocket science. You can go to Minitab and see how to do all this stuff. We're just putting it together. Next slide, please. This is what's unique. I'm now defining this distance. So I'm calling these the probability plot residuals. And they're straightforward to calculate. I have the empirical probability. I've got the scale residual for that specific time. So these are going to be plotting kinds of residuals for me. And then ultimately that plot should form out roughly a straight line. And basically we're using 3 standard error limits. Okay? Why is this valuable to me? It's not valuable for me for this plot. It's valuable for me because now I've got a basis. I can come up with a way of scaling these things so that they've got interpretation. What do we know about maximum likelihood estimates? Asymptotically, there should be following a normal distribution. So if we properly standardize these probability plot residuals, I can get them on a scale where I can determine size based off a standard normal distribution. Oh, it's helpful. Now remember, it's asymptotic, and it's a question of when do the asymptotics kick in. Okay, so it's not precise. It's not like ordinary least squares theory, where we know it's a t distribution. But we know asymptotically it's a z, which is helpful. Okay, next slide. So we standardize them in that fashion. And then I can come up with all sorts of analogs. But ultimately then what we're doing is we're not comparing relative to the curved band. This is taking the curve into account. And now I get plots that are easier to interpret. And I will illustrate. These are the real residual plots for the data that we examined. Okay? So next slide. I did this in R. I'm colorblind, so I'm red-green colorblind, which makes life interesting. 5% of all males are red-green colorblind. Please take that into account. I can see the differences in those colors. Don't ask me what color they are, but I can see differences among them. Too often I go into presentations and people think they got really cool colors and I can't see anything. Literally nothing. The only reason why I know for sure that these are the colors is I specified them in R. Orange, okay? That was for the high stress ratio. I'm a proud graduate of the University of Tennessee in the United States, and they are known as the Big Orange, okay? That's the color. You can't get away from the color orange in Knoxville, Tennessee. I like orange, okay? Supposedly this is red, I have trouble seeing it. And blue, I can see blue. That's the one color I will always be able to see, blue. Okay? So far, so good. But there are a limited range of colors, but I do a lot of R plots with the team so that I can see it. Because I know my team members don't necessarily know what I can see. It's just, the only difference between this and the mini tab plot is that this is a little wider because I made it 3 standard errors. Are we okay? Next plot. But doesn't that look like a normal residual plot that we would see in regression? And what do we do here? I am now plotting the standardized probability residual against the scaled residual. And now I have interpretation. So far, so good? Sometimes I do this. I put the colors associated with it. But in this case, I just did the blues because I've got another plot that will illustrate that. Are we good? You know, when I'm looking at residual plots, I like that. I'm home. I'm a regression guy. Okay? Next slide. Versus target stress ratio. Don't we do it against the regressors? Of course we do. And there's some funkiness here. Are we okay with this? Good. That doesn't seem unreasonable to me. There are a few more failures at the high stress ratio than at the other two, but we came away from this feeling pretty reasonable about it, especially since I don't know when the asymptotics really kick in. The mean value of the residuals is not 0. Understand with ordinary least squares regression, the sum of the residuals has to equal to 0. That's not true here. Okay. Next slide. Versus serial number. So we're trying to see if there's a time effect. Serial number goes back to when the strands were manufactured, and the NASA team actually manufactured the strands. So we have perfect control over that. I don't know if that was a good thing or a bad thing, but we had perfect traceability. I can do any NLO like this, but these are just simple ones that we can look at. So far, so good. And do I have one more slide? No, but what am I trying to show you here? I think next week I'm going to start with a YouTube video of Richard Feynman talking about the scientific method. It's 90 seconds and it blows you away.
9 seconds.
About 90 seconds, minute and a half. But what we're ready to do is we're getting ready to do science. And what happens in science? You propose a theory and you get data and you test the theory. Are we got the idea here? So what was the intent of this lecture? The lecture here was to set up the foundation for the proper analysis to test the engineer's theory. He claims that he has science to back up what he's doing. Actually, it's engineers playing with intervals. And that's a typical engineering model, but that's okay. So what are we going to have to do? We have to be able to compare different models for explaining the data. We have to have that. The purpose of today was to introduce you to how do we analyze a stress rupture model. It's simple linear regression, but with a twist. Now it turns out that for the engineer, the 22 ramp failures are important. So how do we include the ramp failures? And that's where we're going next time. And when we begin to look at those ramp failures, life gets very interesting. Fair enough? So then we get to see the engineer's ad hoc approach and how well it displays the data versus a very rigorous approach, which I will derive for you. I have not seen the rigorous approach in the literature, but we have not done an exhaustive literature search, and that doesn't bother me one way or the other. I don't think it has it here. But we will show you how to approach that analysis. But then it becomes very fundamental. How do we compare a proper analysis to what the engineer wants to do when the engineer is firmly convinced that his theory is the gospel truth? It's fascinating. Are we okay? So the first two lectures were really to set up explaining what I've been doing for 13 years. Okay? I'm happy to entertain questions if we have time.
Yes. And I have a question from Professor André.
Okay.
He is watching us on YouTube. And he is asking, where does the experimental plan fit into the analysis?
Where does what?
Where does the experimental plan fit into?
I'll talk about that next time. But it's going back to the randomization and how we can construct the likelihood functions. But it's there.
Okay.
Yeah, but that's very critical for how we have to analyze the experiment. But essentially, we treat it as a completely randomized design. But I'll talk a little bit about that structure. Okay? Yeah, it's a good question, and I would expect that from Andre.
Yes. Yes. And I have a question.
Yeah.
There you said that you used the two parameter Weibull. Could you have used the three parameter Weibull? What would be the difference?
Let me show you. That's a very good question. I don't know if TCB the time that was censored. So a long time. PC, this is where the censoring occurred. So I've got failures. So far, so good. I can project this out. So if I'm doing just the two parameter models, I've got a separate model for each of the stress ratio. And notice they are two parameters associated with each model. So far, so good? Okay. But now, how does that tie back to the model we fit? So this is the mother model. Those are the 6 parameters. What does the stress rupture model assume? Equals to so I'm assuming that these form a straight line. Okay? And that these are all a common vector. So the mother model says all the information I'm going to use is that I can describe this as a two-parameter model distribution. I can describe this by a second two-parameter model, and the third one here. And I can't get any better in terms of the log likelihood. That's going to that's a true saturated model. These are nothing more than replicas. Are we with that? Okay. But now I can collapse it to the true stress rupture model through this mechanism, which is saying these things line up on a straight line. Okay. That would be the constraint on that. And then I have a common vector. So the three two-parameter distributions give me 6 parameters. And then the stress rupture model gives me 3 parameters, but they can be perfectly related. Okay, so if the true mu's for each one of those individual stress ratios really follow this model, I'm perfectly explaining. The question now is it close enough to that? Because we know there's noise. We know we can't observe those true characteristic lives for each one of the stress ratios. We know there's noise there. So if we can fit that well enough with a straight line, then I don't need all 6 parameters. I can explain everything with 3. This is making sense? And see, most people don't think this way. And the Generalized Linear Models book, even when I'm a co-author, we talk about fit a saturated model, but we don't ever talk about what that saturated model really is. This turns out to be a true saturated model. In a lot of cases, in ordinarily experienced regression, we would have what we consider all the regressors that are candidates. And that becomes our mother model. And then we compare subsets to the mother model. Same thing here. So far, so good? And in fact, I could explain simple linear regression in this framework, in this frame here. I mean, think of a planned experiment. We can always analyze it in terms of the means. Okay? That's what we're doing here. So we've got means, we've got variances. So again, I can have a separate mean and a separate variance for each one of those conditions. We can do that in a planned experiment. Or we can assume that there's some structure there and take advantage of it. And that's where the contrast is. So we never really expect to go with this mother model. It's there for comparison purposes. But it is the best that anybody could do to explain the data. But that doesn't mean it's the best for interpreting the data. It's not necessarily the best for predicting future data. And that becomes the issue. That's the reason why we do things like that penalty in AIC. Because ultimately we're looking at predictive capability. And if we have extra terms that really are estimating 0, we're only inflating prediction variance. And our ultimate goal of this experiment is not to determine the parameters. It's to predict what is the probability of failure at the use conditions for the expected mission line. So prediction variance is very important to us and how that gets transmitted into that probability. This is the proper framework for comparing models. By the way, in Meeker and Escobar's first edition, they don't do any model comparisons. Now, so that's a big advance in their book. You know, for people who are regression people, it's an obvious thing to do. But I have to admit, it dawned on me late in this experience with the engineer. I started doing this about two and a half years ago, using AIC and these chi-square tests. But it's an obvious thing. But you know, what's obvious in area A is not obvious to somebody in area B. And that's a very common issue. And real lucky in my career because I'm broadly trained. It takes me a while. Okay? I grew up in the American South. I still don't like to wear shoes. So, but sooner or later, I might be able to see something over here that goes over here. And that's what we're doing. How can we bring the regression stuff into reliability? How can we introduce the reliability stuff into regression? Both fields, both disciplines, both subject matter areas improve.
Yes, I work with, I told you the time before that I work with a professor from production engineer, and he worked with reliability, but only assume the true Weibull distribution and only don't compare, only use true Weibull distribution.
And if you can estimate it, it must be the
Yes.
truth. You see, that's where my friend gets involved, because he's very creative about, as he says, sometimes you have to torture the data, which is a clue then that he's distorting the data to get the answer he wants. But that's sometimes what an engineer will do, because once they have estimates, they say, well, it must be true. See, I found estimates that work. But now we got to determine, well, okay, how well did you explain the data? And they don't know how to use it. They just don't. If the engineer is relying on maximum likelihood for a well-defined distribution function, life is good. It takes care of itself. Okay? The problem is when it's not clear what the proper distribution function is, or they're trying to do something really creative with the data. Welcome to my friend. And I'll be explaining that next time. Okay? So I've had to stare in the face. How do I explain his ad hoc procedure for combining data? Doesn't work. So I have to do it in a rigorous fashion. And the moment I explain it to him, he just goes blank. And your production manager will probably be very similar to it because they're not trained to think of this thing. So far, so good.
Yes.
One of the people reviewing our final report, one of my PhD students, fully trained mechanical engineer, holds patents, highly respected as a calibration engineer at NASA, who also has a PhD in statistics. He can understand all of these things. He's trained in both of this. The chief engineer for this project initially is also on it, so I think he will be a fair review. But I'm going to hand it to a composites engineer who doesn't understand that AIC actually has some back. My friend actually says AIC is not an appropriate basis for evaluating prediction. Of course, he has no idea what he's saying. He can't justify it, but he will say that. He does say it. And he's saying that that's my opinion as an expert in the area. But he's not an expert in data analysis. See where we're getting into this revolving door. It's fascinating. But this is a complex problem. I mean, there's some of the issues that pop up in complex problems, particularly when you have people who can't really communicate. And we can touch on.
Okay.
Is that cool?
Yes. Yeah.
Yes.
I would like to take a moment. I think that the situation I work with some guys in physics. Generally, they use normal distribution, but I hope to make the introduction of some distribution and make the comparison of this model. So that is situation very common with data of science.
It is, and it's a challenge then to be able to explain how to approach the data properly when they think deterministically.
Yeah. That the other distribution would make an improvement in the results.
It takes patience, it takes a lot of work. And it's a challenge. The responsibility is all on us as the data. but there are 3 PhD statisticians on this team. And there's one engineer who says we're all wrong. And he's claiming to be an expert in data analysis. And it's clear he doesn't know how to analyze data. See where we're going with this. So, but that was the challenge for me, to be able to show proper basis for comparison. Hence the notion of the mother model. He recognizes that the 2-parameter Weibull for each stress ratio is the optimal thing in terms of explaining the data. He understands that. What he doesn't understand is that I established that what we want to do is actually better, in the sense that it's equivalent and less parameters. Actually has better predictive capability. See what I'm saying? Over the head, quickly. That's not what he wants to hear. Okay. After it's all done, I can tell stories that are a lot of fun about how he would make decisions sometimes. But now we have the opportunity to establish here's the proper way for approaching the problem. It took a long time. And see, this is my summer vacation. I'm having fun trying to explain this thing. Oh, it's cool stuff. I'm having fun. Okay?
Okay, so let's think. Então, a gente está finalizando o seminário de hoje. Muito obrigada aos que nos acompanharam pelo YouTube. Boa tarde.